5,000 gauss, the rest of the power can be maintained through the copper. So the key thing here is that as long as it's under, in other words, I just put enough turns around this very, very large ferrite core, so that basically it would hold up the, keep the magnetic flux low enough at 20 kilohertz, such that basically Wesley could reach a peak flux density of somewhere like around 1,500 gauss. So his headroom goes up to 5,000. So that's a bit of headroom, and the rest of it is just current. So in other words, as long as the wire can withstand it, and at the voltages that he's at right now, the secondary wire is 24 AWG, which is about 0.6 millimeters of wire, and the primary is foil. It's a flat foil. So that's also, and the foil is about how many millimeters? Maybe about 15 millimeters wide and by 2 mils thick. So it's a pretty heavy-duty primary winding there also. So you can get a fair amount of power through this transformer.
Apparently, you do not expect the core to saturate because they didn't provide an air gap. But then again, I think this is part of the feature that is looked for to create those eddy currents that will do more damage to the sparks than you might believe. But anyway, I was wondering, how did it isolate between the layers? The top layer must be under a tremendous stress for isolation.
Yeah, it's interesting. See, there's a lot of surface area around this core because each side of the core is about 5-inch length. So I have 4 sides of 5-inch length, and the number of turns per side, one side has got basically 50 turns of secondary. The other side's got 70 turns of secondary, 50 and 70. So that's the 4 sides. And between primary and secondary, the flat foil, which is underneath the bottom, and then the other gauge wire is just right on top of it, is separated by Kapton tape. So the Kapton tape is basically a triple insulated system. So in other words, the insulation system is good to maybe about 230 degrees C, and the 5 mil.
And don't cut them in one line.
For at least 5 to 8,000, and there's 3 layers. So in each turn is only a maximum of 40 volts per turn. So it's really not that much stress on the.
So now I have this sleeve.
Corona buildup.
It's a final stage of assembly. The signal comes from the signal generator through the fluke from here to glance transformer. From glance transformer goes in, I have from the other side, this is the output of the glance transformer, goes to 2 independent measurement points that I can put my high voltage probe into it. Okay, that's for this purpose. So I can easy switch and eventually put to one side of Avramenko fork and the other side of Avramenko fork. That's what I can do. So I'm gonna put it away. Then ground terminal, a switch to disconnect the power to Avramenko fork. One side from Avramenko fork goes to the spark gap, through the spark gap, and then goes to caduceus. The other side goes directly from the caduceus, goes directly to the glance transformer. The reason that I use this, keep the wires away from each other. In most of the application I use a heavy high voltage 15,000 volts wire, but this is also high voltage wire as well. Now I connect these capacitors in parallel in here, and from this side I took each one of the wire, deliver it to one single point, and that gives me ability to control the capacitance on the terminals. of output of Avramenkov work. The second bank of diodes is in here, brown one. The diodes. One side of the bank of diodes is connected to this terminal, and from this terminal goes to the pickup coil, the side that is close to the caduceus. And the center lead is connected in here, but I didn't connect it yet. Oh, this capacitor is a beauty. Made it myself. One day of work, not even one day of work.
Sir Plastic was ready to buy a dead size. I looked for the plastic screws with the sleeves. The sleeve is exactly the thickness of the capacitor. The screw goes inside the sleeve.
I can control the capacitance by simply shorting the leads in here. The screws are not the metal screws, they are plastic screws from Home Depot. The plastic is from Home Depot, and the foil is from Home Depot as well. This is the foil, flash guard. That's what it says in here. When you unroll it, it looks like that. It's not really a thick one. You can bend it. Paper on one side. Dick, Glenn, Eric, and John. Thank you very much.
Well, the critical point is the leakage at the end of the layers. This is where most of the damage is done. So did you use progressive smaller layers, or you use the same width of the layers all throughout? So how do you prevent from leakage from layer to layer across the pump?
Single layer transformer. All the windings share the same layer of magnetic flux. Isn't that something?
This is a step-up transformer. You push in, I don't know, 10 volts, and you get out 20,000 or whatever volts, 10,000 volts. You have one single layer here? That's interesting.
Imagine that the transformer were a toroid. It's very close to it. Even though it's square, it's very, very close to toroidal in design. So if you put the windings interleaved, which are basically what they are, the windings are actually interleaved on a single magnetic layer. So in other words, as the windings go around, they're in between each other. Do you follow now?
Not really, because that means that you have to segment the wire. You cut the wire and then to solder it again. I don't think you did that.
What I had to do is send you a photograph. A photograph would explain everything. If you see the way that it's actually ran across the core, the magnetic layer is actually, I calculated the area.
Let's come back for a moment to the stage number 2. I showed you before stage number 3. Let's see the details. The rear connection to the metal plate, the front connection to the metal plate. Look at the capacitor that could be variable capacitor instead of the fixed one, the switchable one, next to the bank of the capacitors. The wire, the thick wire in the mold that you see is the wire, the ground wire connected to the metal plate at the rear of the plate. On the right hand side and left hand side there is a spark gap tube. There is no need to use this kind of tube. Air spark gaps are okay. I just had them, I was trying to experiment with them. The capacitor does not have to be, again, switch bank of the capacitor could be variable one. But it is hard to get one that has big enough capacitance and still will be variable at big cap for high voltages. The coaxial cable I have used for the connection between transformer, which is being called Glenn transformer. A brilliant American engineer, one of the 15% of the most knowledgeable people in the world, who designed the transformer for me. That resistor that is shown in here doesn't have to be used. It was only for the experimental purposes. The connection to the generator. A remnant fork.
So what I'm doing right now is I'm looking for the light bulb, for the socket. Oh boy, where did I put it?
4 bars of
Secondary.
material assembled in a square, where basically the core itself is being used as the bobbin.
If your last sentence produces an image in my mind of a layer that is one wind width, but very tall. So this construct would create a bobbin, a vertical bobbin rather than horizontal bobbin. Is that what you're saying?
It's all resting on the core material underneath it. So basically what's happening is the cross-sectional area of the transformer has both the primary and the secondary following each other around the magnetic material.
Okay, that seems to be a very interesting construct. Why going to that pain? Why not a regular transformer? Is there anything special about this construct?
Well, I think the problem that Wesley was looking at was that he was trying to create a rise and fall time. He has a generator right now, a fluke generator, that will go from basically 0 to 1 kV relatively quickly. I'm not sure of the exact specifications of this amplifier that moves the waveforms up and down. And he tried loading other transformers on the output, and of course, because of poor coupling or air gaps in transformers and other things, he wasn't able to couple the energy and get the step up that he was looking for. So I designed a transformer that would give him extremely low leakage inductance and give him a ratio of 10 to 1 in the transformer, and at the same time be able to maintain a very, very high efficiency, or having a voltage coefficient or coupling that's better than 99%. So the coupling coefficient in this transformer is about 99.8, 99 point almost 9% voltage coupling.
Right. However, I understand that Wesley had a waveform problem. In other words, rising and falling edge not being what he wanted to. But this is a function of the inductance and the capacitance into the mutual coupling of the wires. So to minimize that, I really don't know. I have to see it. All the transformers will behave like that, Glenn. It might be resonating on one frequency in which the waveform is preserved, but I doubt it could be fruit banded. I really don't know. But congratulations, you did some good job there apparently. Back to you.
Well, I did some measurements on the transformer, and I was looking at on time or pulse widths of 2.5 microseconds, and varying the off time from 20, let's say 22 and a half microseconds of off time, and then they started narrowing it into a 50% duty cycle. There was 2.5 microseconds on, 2.5 microseconds off, for a total of 500 microseconds in period. So I was varying between, say, 20 kilohertz to 500 kilohertz with just a fixed on time of 2.5 microseconds. And in doing so, I was able to watch the rise and fall times of I have a very, very staunchy generator, and my generator was able to maintain approximately 350 nanoseconds of rise and fall times in the voltage ranges of 1 kilovolt. So I think so basically whatever distortion was on the primary was on the secondary and vice versa. I didn't see any dissimilarity between primary and secondary, which is really, I think, what he was looking for.
Okay, so the best fall time that you achieved was 300 nanoseconds?
Yeah, on the basically what was happening was the limitation was my generators. I didn't have generators that could really force 1 kilovolt in less than 350 nanoseconds. That was basically the limitation. And realistically, what was happening was my generator was really only 100 volts. So my generator was able to generate the square wave pulses, 0 to 100 volts in about 350 nanoseconds. But when I looked at the secondary, and I was looking at the rise and fall times, which was basically a 10 to 1 ratio of 1 kilovolt, the 0 to 1 kV was also in the order of 300 nanoseconds. So that's when I decided that my coupling was very good.
Yeah, it escaped me that primary is a 1,000 volt pulse. This is quite high. You need a very special power generator for that. Okay. Well, I think Wesley now is suckling that little baby and doesn't want to let it go, right?
Yeah, I mean, if he wants to get good square waves at at the 10 kilovolt area, I think this will do it for him. Right now I think it's probably the least expensive way of him getting there, because right now he does have a generator that will go to 1 kV, but to get to 10 kV he needs something there to step it up. So I'm pretty sure that in the currents that he'll be using are very, very low. So I would imagine as long as his generator doesn't saturate, he should get the waveforms that he's looking for.
A spark gap generator will not be good enough for him?
I think what he's doing right now is he's using like a regular signal generator that generates a train of pulses that will give him like 0 to 1 kV. And then basically this transformer is going to go on the output of that to get him up to 0 to, or not so much 0 to 10 kV, but maybe, let's say, plus 5 kV, minus 5 kV, at least in the 100 kilohertz area. And then he'll be able to drive his diodes and his spark gaps and all the other good stuff on the other end, and then accurately adjust his pulse widths and, see what the correct waveforms in a lab manner, if you know what I'm saying.
Okay. It seems quite a convoluted system. I solved my problems for free energy. You know what I'm doing here?
I'm not sure, but the best mechanism for free energy is a good pair of battery cable jumper leads and some long heavy wire, and you run it back to your house from the power lines outside around your power meter. What did you do, Alex?
Well, this is true, and many of Romanians are doing that. I did something more sophisticated. I installed a little dynamo on the cold water.
Okay, starting from 10 kilohertz, because this device works only from 10 kilohertz to 150 megahertz. We have a nice flat relation between phase and gain. That means line magnitude. I'm sorry, logarithmic magnitude. So I'm going right now. As you see, right now I'm at 125 kilohertz. Still is flat. Beauty. Flat. The phase keeps about the same. No changes. 200, 700, 278. Now in here we are approaching the point where still is 147 degrees the phase. Let me compare it to what was 177. In here we have a 63, so the rapid change we have somewhere in the vicinity of 479 kilohertz. The most important for me is the green line. So up to that point, the green line is, I'm sorry, no, the green line is phase, the log magnitude, the yellow line is approaching the maximum in here. So we have minus 731 dB, and then it goes down, down, minus 31, at the frequency of 538. So I'm gonna come back to that point, minus 7.3 dB. Okay, what's gonna happen when I treat that with Smith chart? So that would be R plus JB. Oh boy, this is nice. I like it. Microhenry, 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 microhenry. We're going to that point, and then all of a sudden it changes nanofarads. Okay, so now when it goes to this line, from here down shows a capacitance, from here up shows inductance.
So what it looks like, the output of the transformer shows at a certain frequency more inductive character or more capacitive character. Of course, I have to consult that with Glenn and Dick to make sure that I'm reading it right. Okay guys, have a good night. Talk to you soon.